Hey, glad you could join us. Thanks for making a little space in your day for something quiet and cosmic. I hope you're somewhere cozy right now, maybe with a warm drink or the sound of rain in the background. It's always nice to know someone out there is listening in peace. If you're settling in to drift through the stars with me, you're in just the right place. I really appreciate you being part of this gentle little journey. You being here matters. Hey everyone, today we're looking into stars and into time itself. Not just how stars live and shine, but how time, that quiet, invisible river we're all drifting through, behaves when we push against the edges of nature. We're going to explore why time slows down at light speed. It might sound strange, but by the end of our voyage, it'll feel as real as the warmth of starlight on your face. Take a slow breath. Feel the quiet pull of space around us. Let's leave Earth behind gently. No rockets, no countdowns, just a silent lift as gravity loosens its grip. Below us, cities grow small and the clouds stretch out like soft ripples in a blue ocean. Up here, it's quiet, peaceful, you and me, just floating. As we rise above the planet, time is ticking along as usual. Seconds pass one after another like footsteps on a long walk. But here's the thing, time isn't fixed. It isn't like a drum beat you hear at the same pace everywhere. Time can stretch, time can slow, and when we move faster, closer to the speed of light, that's exactly what it does. Let's ease toward that thought, gently. Imagine we're drifting beside the International Space Station. You can wave at the astronauts inside, they're circling Earth at over 17,000 miles per hour. At that speed, their clocks tick just a tiny bit slower than ours on Earth. Not enough to notice, not enough to feel, but it's there. They age just a little more slowly. Time is passing differently for them than for us. Strange, right? Now let's push a little faster. Picture yourself in a sleek, silent ship. No noise, just a soft hum, like a whisper from the stars. We start to accelerate. Faster, 1,000 miles per second. Then 10,000. The stars begin to stretch slightly, the light bending, colors shifting like oil on water. And something else starts to happen. Time inside our ship begins to slow down. It's subtle at first. A second out here feels like a second to us. But for someone watching from Earth, our movements are starting to seem sluggish, like we're walking through honey. Not because we're tired, not because we're lazy, but because time for us is literally moving more slowly. This idea might feel slippery, so let's sit with it a little longer. Reach out and feel the controls of the ship beneath your fingertips. Look at the stars ahead. They still sparkle. The universe feels the same. But behind us, Earth is aging a little faster than we are. If we kept accelerating not even halfway to the speed of light, decades might pass for people on Earth while only a few hours pass for us. And if we kept going, if we could reach light speed, something wild would happen. Time for us would slow all the way down. Now don't worry, we can't actually reach light speed. Not with any ship, no matter how futuristic. But we can imagine what it would feel like. That's the magic of this journey. And in imagining it, we uncover something profound. Let's drift beside a beam of light for a moment. Light doesn't experience time the way we do. From the moment it leaves a star to the moment it touches your eye, no time passes for the light itself. It doesn't feel like it traveled for years or centuries or even seconds. It just exists, instantly, in its own kind of eternity. To us, it takes 8 minutes for light to get from the sun to Earth. But for the photon, no time passes at all. That's the strangeness of light speed. That's what we're exploring. Picture yourself floating beside a photon. It's not hot or cold. It doesn't have a face, but it's heading somewhere fast. The fastest anything can go. And from its point of view, the beginning and the end of its journey are the same point. No waiting, no aging, no clocks ticking inside the beam. Just movement without time. That's what it means for time to slow at light speed. And it's not just a metaphor. This isn't poetry, though it feels like it sometimes. It's real. It's been tested in particle accelerators, in atomic clocks flying on jets, in satellites circling Earth. Time really does stretch and shrink depending on how fast you move and how deep you are in gravity's pull. Let's drift beside a GPS satellite for a second. High above Earth, it's helping people find their way whether they're walking through a city or flying across oceans. But did you know those satellites have to account for time ticking differently up there? Because they're moving fast, and because gravity is weaker higher up, their onboard clocks run slightly faster than clocks on Earth. Engineers have to adjust for that so your phone knows exactly where you are. So you see, we're already living in a world where time isn't fixed. It's elastic, it bends, it flexes, and it does so because of two things: speed and gravity. We'll explore gravity next. It has its own way of playing with time. But for now, feel us accelerating once more, not with force or pressure, just a gentle surge forward. Stars streak just slightly at the edges of vision. Time inside our ship slows further. From Earth's point of view, we're starting to stretch like molasses. But to us, everything feels perfectly normal. We talk, we blink, we breathe just the same. That's the beautiful twist. You never feel your own time slowing. It only happens compared to someone else. And that's why time slowing at light speed isn't just about speed. It's about comparison, perspective. Two travelers, each with their own experience of time, depending on how fast they're moving and where they are. Let's hover now beside a pulsar, a spinning remnant of a dead star. It flashes like a lighthouse, perfectly regular, again and again. From a distance, you can count the pulses. But if you flew near it at high speed, those pulses would seem to slow, not because the star changed, but because your time changed. Everything in the universe dances to time's rhythm, but that rhythm isn't the same for everyone. Now imagine if you went on a journey at near light speed, left Earth for a distant star and came back. For you, only a few years might pass. But back on Earth, decades could go by. Friends would be older, maybe gone. Cities would have changed. This isn't science fiction, it's time dilation. It's real. Feel the weight of that. The loneliness, the wonder, the incredible strange truth that time, the thing we think of as absolute, is anything but. So, why does time slow down at light speed? Because the universe has a speed limit, the speed of light. Nothing with mass can reach it. And as you get closer to it, everything changes. Your momentum increases. The energy needed to go faster climbs sky high. And to balance it all out, time begins to slow for you. It's the universe's way of keeping things in harmony. Time is like a soft, stretchy fabric. The faster you move, the more it stretches around you. And at light speed, it stretches so far, so thin, that it nearly stops altogether. But don't worry, time will pick back up again when we slow down. And we'll explore that next. The return, the ripple, the way time catches up again. If you enjoy quiet space stories, tap like to help others find this peaceful place. Subscribe for more calm journeys through the universe, and let me know in the comments where you're listening from and what time it is. It's always fascinating to see where you're all tuning in from across the world. Still with me? Good. Let's keep going. Out here, where the stars whisper and the silence wraps around you like a soft blanket, time feels like it's holding its breath. But even in this stillness, there's motion. The galaxy is rotating. Planets are orbiting, and we're still gliding forward, gently pressing closer to that impossible edge, the speed of light. Now, let's look around together. See how the stars ahead seem a little bluer. That's not your imagination. It's something called blue shift. As we move faster toward the light coming from those stars, the waves of light get squeezed together like footsteps bunching up as someone runs toward you. The colors shift toward blue because blue light has shorter wavelengths. That's the light's way of telling us, you're getting closer. Behind us, the opposite happens. The stars fade redder. That's redshift. As we move away from their light, the waves stretch out, growing longer and redder. Eventually, if we keep accelerating, they'll stretch so far we won't see them anymore. They'll disappear into the infrared, then into the microwave, and finally into radio waves, too faint for our eyes or ears. This is the universe's visual language, quietly reminding us how fast we're moving. And as light shifts, time shifts too. You might be wondering, how do we know this stuff is real? It sounds dreamy, poetic almost. But it's not just theory. We've tested time dilation with particles, tiny ones called muons. These muons are born high in Earth's atmosphere when cosmic rays hit, and they zip downward at incredible speeds. They're unstable, they decay quickly. Normally, they shouldn't survive long enough to reach the ground, but they do. Because they're moving so fast, time for them slows down. From our perspective, they live longer than they should. That's time dilation. happening right above our heads, every single day. And then there's the Hafele Keating experiment. In 1971, scientists flew atomic clocks on airplanes first eastward, then westward. When they compared those flying clocks to clocks on the ground, they didn't match. Time had passed differently for each one. Speed changes time. Elevation does too. Even being higher in a gravitational field like on a plane lets time run a tiny bit faster. Tiny differences, yes, but the universe notices, and so do we once we learn how to listen. Let's float now above a neutron star. See that dense little point spinning wildly below us. It's about the size of a city, but heavier than our sun. The gravity here is immense, billions of times stronger than Earth's. If you dropped a marshmallow from a few feet up, it would strike the surface with the force of a bomb. That's how dense this thing is. And because the gravity is so strong, time down there moves slower than it does up here. That's not science fiction. That's general relativity. Einstein showed us that gravity bends space and time like a heavy ball sinking into a soft trampoline. The deeper the gravity well, the slower time flows. So even without moving fast, just being near something massive changes the way time behaves. Now blend that with speed, and things get even stranger. Let's step into a thought experiment. You and I, inside our ship, accelerating smoothly through space. Everything feels normal. We're chatting. You smile. Maybe you sip something warm. But outside to someone watching us, we're slowing down. Our speech, our gestures, our very lives are unfolding in slow motion. And what if we accelerated more? Well, here's something surprising. As we near the speed of light, not only does time's slow distances compress, the universe in front of us starts to squish inward. It's called length contraction. We don't feel it from inside the ship, but an outside observer would say the space ahead of us has shrunk. So what's really happening? From our view, time feels normal. From theirs, we're crawling through a flattened universe. Both are true. That's the beauty and the weirdness of relativity. Let's fly now alongside a particle of light again, a photon born in the belly of a distant star. Maybe it formed 1 billion years ago, in the heart of a burning sun somewhere near the edge of the Virgo cluster. From its own point of view, it was born. And then, it arrived here, instantly. No passage of time, no journey, no delay. For the photon, creation, and arrival are the same moment. This is hard to imagine because we live inside time. We measure our days with clocks and calendars, birthdays and sunrises, but light doesn't experience time at all. And the closer we get to light's speed, the closer we come to that timelessness. Now feel that paradox with me. Time is slowing down, and yet everything inside our ship feels the same. That's the heart of time dilation. You never notice it happening to you. But step outside, compare yourself to someone who stayed behind, and the difference is astonishing. Let's say you left Earth for a star system 100 light years away. You travel at 99.9% of light speed. To people on Earth, your journey takes a little over 100 years. But for you, it might feel like just a few years. You'd return home to a world that had moved far ahead without you. Friends aged, cities changed, trees grown and fallen. A future that arrived without you there to watch it unfold. It's beautiful. It's unsettling. It's true. And this is why we say time slows down as you approach light speed, because compared to the people you left behind, it truly does. Let's hover now beside the glowing rings of a black hole. The gravity here is intense. It pulls not just matter, but time itself inward. Near the edge, the event horizon time slows so much that to an outside observer, anything falling in seems to freeze. They'd never see it cross the edge. It would just hover there forever. But from the falling object's point of view, time feels normal. It crosses the horizon and falls inward. What happens next? We don't fully know. But the lesson is clear. Time's flow depends on where you are and how fast you're going. It's not universal, it's personal. Even light isn't immune. If you tried to shine a beam upward from close to a black hole, the light would lose energy as it climbed. It would stretch redshift, growing colder, dimmer, more tired. Time and energy are woven together. When one bends, the other follows. Feel the stillness with me now, the hush of space, the slow dance of time as we skim the edge of the cosmic speed limit. The universe doesn't rush, it doesn't force, it simply allows. And the closer we get to light speed, the more we notice time unraveling from our usual pace. It's like trying to run underwater. You feel the resistance, the distortion. Except here, the distortion is in the very rhythm of seconds and minutes. Why does time slow down at light speed? Because the universe protects its boundaries. Because no one gets to break the cosmic speed limit, not even us, in this imagined ship. As we approach that limit, time yields. It slows. It bows out gracefully, making sure the rules stay unbroken. And what would happen if we actually reached light speed? Well, we can't. At least, not with mass, not with ships, not with bodies. But let's dream anyway. If we could, time would stop completely. The universe ahead would shrink to a point. Everything else, all of space and time, would vanish from our view. There would be no before or after. No movement, no change. Just a single instant, stretched forever. But that's not a place for us. It's a place for light alone. So instead, we glide close as physics allows, and feel the shift, the slowdown, the strange beauty of a universe that plays with time like an artist with paint. Let's rest here a moment. We're deep into the folds of time now, still together, still drifting. And there's more to see. Still floating beside me? Good. Let's keep going. You and I, side by side, easing through the quiet dark, watching time behave in ways it never would back home. And here's something that might make you pause for a moment. Speed and gravity don't just affect time, they reshape what we mean by now. In everyday life, we all agree on what now means. You and I can look at a clock and say, this is now. But out here, especially when we're moving fast, that now becomes slippery. Imagine we're zipping through space at near light speed, and you look back toward Earth. The people you left behind, the ones sitting in gardens, walking dogs, falling asleep under city lights, their now doesn't match yours anymore. Depending on how fast you're moving and in what direction, your definition of now might stretch into their past or their future. That's not science fiction. That's the relativity of simultaneity. Time itself becomes relative, not just how fast it ticks, but what moments exist at all. That's one of the wildest consequences of approaching light speed. The idea of when gets as bent and strange as space does around a black hole. And yet, from inside the ship, from inside our moment right here, everything feels calm. That's always the trick with relativity. It doesn't feel dramatic from within. You could live your whole life at high speeds and never notice time slowing for you until you came back and realized the world moved on without you. This isn't just an idea we've played with in theory. We've proven it over and over again. The International Space Station orbits Earth at about 17,000 miles per hour. It's not anywhere near the speed of light, but even at that modest velocity, astronauts age just a little bit slower than we do. Not enough to notice. Of course, just milliseconds. But if they stayed up there for decades, the difference would grow. Extend that to spacecraft moving at 99% the speed of light, and suddenly, decades pass for everyone else while only a few years pass for you. Time becomes elastic. And it gets even stranger when you think about energy. The faster you go, the more energy you need to go even faster. It's not a straight line. If we wanted to go from 90% to 99% of the speed of light, we'd need twice as much energy, then twice as much again to go from 99 to 99.9. And it keeps going. The closer you get to light speed, the more energy it takes until it becomes infinite. That's why no object with mass can reach the speed of light. Not because the universe says no exactly, but because it gently, stubbornly says, you'd need everything, every bit of energy that exists, and even then, it still wouldn't be enough. So instead of hitting the wall, we curve around it. Time bends, mass increases, distance shortens, and the closer we come to light speed, the more those effects intensify. Think of it like approaching a horizon that keeps receding, never letting you touch it, but always reminding you it's there. But again, from inside, everything feels normal. That's why it's so strange. You don't feel your own time slowing. You don't notice the universe ahead collapsing inward or the stars behind stretching out. It's only when you compare notes with someone who stayed behind that the difference becomes staggering. That's the part that gets me every time. The universe doesn't shout. It doesn't flash neon signs saying, "Look, time is slowing." It just quietly, patiently bends the rules while making sure you never notice them until it's too late to go back. And all of this, the stretching, the bending, the dilation of time itself, is baked into the structure of reality, not a bug, a feature, built into every beam of light, every turning planet, every whisper of a quasar on the far edge of the observable universe. Speaking of which, let's look out that way now. The observable universe. From here, it looks like a sphere about 93 billion light-years across. That's the part of the cosmos we can see, the part whose light has had time to reach us. But beyond that, we don't know. Probably more universe. Maybe infinite. Maybe curved back on itself in ways we can't detect. But here's the kicker. The edge of the observable universe isn't a wall. It's a limit of time. The farther we look, the farther back in time we're seeing. Those faint smudges of light we can barely detect. Some of them come from galaxies that no longer exist. Their light took billions of years to reach us. And in the time it traveled, those galaxies changed or died or drifted beyond our ability to see them. So light doesn't just move, it carries memory. And as we near light speed ourselves, we start to share in that timelessness, that strange ability to move without aging, to travel without time passing. It's what gives the speed of light its haunting magic, not just as a limit, but as a bridge between now and then, between here and the farthest reaches of the cosmos. Let's float here for a bit, you and I, and look around. See that faint blue smear on the edge of your vision? That's a quasar, the blazing heart of a young galaxy from billions of years ago. Its light has been traveling all this time just to arrive here, now, beside us. If we were moving fast enough toward it, that light would appear even more blue, even more intense. The quasar's past would rush into our present, and our clocks would tick slower than the ones back home. That's the link again. Speed, light, time, always connected, always dancing around each other in an endless cosmic spiral. And the deeper you go into this dance, the more you realize time isn't a fixed river, it's a fabric. A flexible, stretchable, sometimes twistable thing. The universe doesn't treat time the way we do. It doesn't divide it neatly into seconds or minutes. It doesn't mind if your clock says 10 and mine says 12. All it cares about is relative motion. Who's moving faster? Who's deeper in a gravity well? Who's coasting through the cosmos with massless perfection? And right now, we're learning what that means, not from a book, not from an equation, but from drifting together through this vast, slow ballet of relativity. You with me so far? Still cozy in your seat? Still wrapped in whatever moment you brought with you? Good, because where we're going next gets even stranger. Not weirder in a science fiction sense, just more deeply real. Because the truth is, the closer we get to light speed, the more we become untethered from time itself. We don't just experience less of it, we experience it differently. There's a symmetry to it. The laws of physics don't care how fast you're going, as long as you're not accelerating. But as soon as you change speed, as soon as you speed up or slow down, time stretches in your direction. It's like the universe hands you a little time credit for moving, or maybe it's a penalty, depending on your point of view. But it's not unfair, it's not arbitrary, it's precise, predictable, elegant. And that's the most beautiful part of it all. The universe is weird, but it's never messy. And that brings us closer to something truly strange. We've seen stars run out of fuel, we've watched galaxies fade into the distance, and we've hovered near black holes, but none of that tells us what happens to time itself as we get closer to the speed of light. So let's slow down for a moment and begin to feel the mystery unravel. Imagine we're floating beside a beam of light. It's not something you can really touch or hold, but you can almost feel it, a kind of perfect energy, moving faster than anything else in the universe. Light moves at about 300,000 kilometers per second. That's fast enough to circle the Earth more than 7 times in a single second. And here's where it gets interesting. If you were somehow able to ride that beam of light, if you could drift alongside it without ever falling behind, something deeply unusual would happen to time. For you, time would begin to slow down. Not a little bit, but dramatically. Let's say you and I are holding hands, and you take off in a spaceship that moves very, very fast, just shy of the speed of light. I stay behind, floating in space with a calm thermos of tea. You travel for what feels like only a year to you, but when you come back, I might have aged 10 years, or 50, or 1,000. It all depends on how fast you were going and how long you stayed away. You would come back looking exactly the same. Meanwhile, everything you left behind, your friends, your home, even whole civilizations might have changed completely. This isn't science fiction. It's real. We call it time dilation. The faster you move, the slower time ticks for you compared to someone standing still. And it's not just a theory. We've measured this with satellites, with fast-moving particles, even with atomic clocks flown in airplanes. Time really does slow down as you go faster. Not just in an imaginary sense, literally. Let's float near a fast-moving object now, a spaceship, sleek and silent, zipping past a star at an incredible speed. If we could look inside, we'd see the clocks inside ticking more slowly than ours. The people aboard feel normal. Everything feels ordinary to them. But from our viewpoint, their time is stretched out. It's like their entire ship is moving through time in slow motion, even though they don't notice it at all. The closer something gets to the speed of light, the more intense this effect becomes. If they reached exactly the speed of light, which, to be clear, no object with mass can do, time would stop completely. From their perspective, the universe would freeze. No seconds would pass. It's as if the future and the past would collapse into a single, endless moment. This idea isn't just poetic, it's rooted in the nature of space and time themselves. You see, space and time aren't separate things. They're connected, woven together into something we call space-time. You can move through space left, right, up, down, and you also move through time second by second, but there's a kind of trade-off. The more you move through space, the less you move through time. So if you're sitting still, like you are right now, you're moving through time at full speed. But if you start to move faster and faster through space, your movement through time slows down. This isn't a metaphor, it's the way the universe really behaves. Space and time bend and stretch together, like a soft fabric that adjusts depending on how you move. You might be wondering, how do we know this? We've seen it happen with particles called muons, which are created high up in Earth's atmosphere. These particles move so fast that they should decay in microseconds before ever reaching the ground. But they do reach the ground, because time is slowed down for them. They live longer from our perspective, simply because they're moving close to light speed. It's like watching someone sprint across a tightrope, but from where you're standing, their steps are drawn out, like they're running through honey. The muons don't know anything strange is happening. They live their little particle lives and decay when they're supposed to, but we see their journey stretched out, as if time had paused for them along the way. Picture yourself now gliding beside one of those muons. You're moving with it, high above the planet, racing toward the surface. Around you, the air is thin and glowing, the upper atmosphere humming with energy. The ground rushes closer, but time feels calm, gentle, stretched. Everything below is still moving forward, cities waking up, oceans shifting, clouds forming patterns, but up here, in this razor-thin slice of high-speed motion, everything feels slower, like you're outside of time's usual rhythm. That's what motion does to time, and the faster you go, the more time lets go of its usual pace. Let's drift even faster now. Not to the speed of light, we can't quite touch it, but very close. Imagine you're in a ship accelerating to 99% of light speed. At first, the stars outside rush past you. Their colors shift. The light in front of you turns bluish, while the light behind you shifts toward red. This is called the Doppler effect, and it's the universe's way of showing you that even light has to stretch and bend to keep up with your motion. Time inside your ship is moving incredibly slowly compared to the outside world. If you stay in that fast-moving state long enough, you might travel for what feels like 1 hour, but decades would pass back home. And here's something even stranger. This isn't just a trick of perception. Time isn't pretending to move slower, it really is. For you, the hour feels perfectly normal. You eat a snack, take a nap, maybe read a few pages of a good book, but for someone watching from the outside, your every motion is stretched. Your blinking, your heartbeat, even the ticking of your clock, it all moves more slowly. You are experiencing time differently. Time itself has changed for you. And yet, everything still feels natural, because that's how time works in your frame of reference. The universe never makes you feel like you're doing something strange. It just adapts around you. Isn't that wild? It's like the universe has a hidden rule. Move faster, and it will gently dial back the speed of time for you. No alarms, no warnings. Just a smooth, silent shift. You might not even realize it unless you stop and compare notes with someone who stayed behind. And by then, they might be long gone. Time has many speeds, depending on how you move through space. Light moves so fast that it experiences no time at all. From a photon's point of view, if it could have one, the journey from a distant galaxy to your eye happens in zero time. It leaves the star and arrives in your retina instantly, from its perspective. To us, that journey took millions or even billions of years, but to the light, it was over before it began. That's the mystery we're holding in our hands here. Time, that slow and steady pulse we take for granted, is far more flexible than it seems. The closer you move to light speed, the more time bends, softens, stretches, until, at the very limit, it stops altogether. And there's so much more to discover. Now, let's sink even deeper into this mystery. You're drifting beside me again, and the stars are starting to thin out. Not because they're disappearing, but because we're moving fast, incredibly fast, and the universe itself is beginning to blur. You might notice something strange now. The sky ahead is brighter and more concentrated, and behind us, it's darker, stretched. That's time dilation making its mark not just on your clock, but on the very light around you. You're not just moving through space, you're curving through time. We're approaching a kind of cosmic edge where time and light begin to twist together like threads in a rope. The faster we go, the harder it becomes to separate one from the other. But before we push further, let's go back to a calm, slower moment. Picture yourself sitting still, in your cozy place, breathing evenly. Right now, time is flowing at full speed for you. Every second that passes is just a second, no slower, no faster. But even now, light is racing past you at its full pace, completely unaffected by your stillness. It always moves at the same speed, no matter what. That's part of what makes all this so strange. Because unlike everything else in the universe, light doesn't speed up or slow down for anyone. You can run toward it or away from it, but it doesn't care. Its speed is constant, and that's the clue that tells us why time changes when we start chasing it. See, for the universe to keep the speed of light constant for everyone, whether you're standing still or moving near light speed, something else has to give. That something is time. To keep light consistent, time has to flex. It's like the universe saying, "All right, I'll slow your clock down just a little, so this light beam still looks the same to you as it does to everyone else." And that's not just a poetic way to say it. It's exactly what happens. Your perception of time literally slows down, and not just yours. The clocks you carry, the atoms in your body, the rhythm of your thoughts, they all shift, because to preserve the balance, time must stretch. Let's pause and float near a real-life experiment. In orbit around Earth, there are satellites that carry ultra-precise atomic clocks. We use them every day, without thinking they're part of the GPS signals in our phones, guiding us from place to place. But here's what's fascinating. The clocks on those satellites tick slightly faster than clocks on the ground. Why? Because they're moving faster, and because they're further from Earth's gravity. Both speed and gravity affect time, so those clocks need to be adjusted, ever so slightly, to keep our GPS maps accurate. If we ignored that time difference, GPS would quickly become useless. That tiny tweak, that tiny sliver of time, proves that time isn't a universal constant. It changes depending on where you are and how fast you're going. Now imagine you and I are drifting far from Earth, passing by a spinning neutron star. These dense remnants of ancient stars are so compact that a single teaspoon of their material would weigh billions of tons. The gravity here is intense. It bends light, distorts space, and yes, slows time. If we hover just above the surface of that neutron star, our clocks would slow down compared to clocks floating in deep space. To an outside observer, we'd seem frozen, barely moving, while for us, everything would feel normal. That's gravitational time dilation. Just like motion can stretch time, so can mass. Let's combine both now. Imagine a spaceship skimming the edge of a black hole, circling faster and faster, hugging the boundary called the event horizon, the point where even light can't escape. Here, both effects collide, the immense gravity of the black hole and the high velocity of the ship. Time slows to a crawl. For us inside, hours might pass, but for the rest of the universe, eons rush by. Galaxies form, stars die, civilizations rise and fall, and still we orbit, unchanged. It's a dizzying thought, but not a fantasy. It's real physics. The closer you get to intense gravity or extreme speed, the more time stretches. The universe bends the rules just enough to keep its deepest laws consistent. Let's look at it from another angle. What if you could travel at 99.9999% the speed of light? From your perspective, your journey might last a few weeks, but when you return, millions of years could have passed back home. Forests might have turned to deserts, cities to ruins, mountains might have crumbled into dust. To you, the journey was short. But for everyone else, you were gone for ages. This is called the twin paradox. It's a thought experiment, but one grounded in real physics. Two twins, one stays on Earth, the other goes on a near light-speed trip. When they reunite, the space-traveling twin is younger, not just metaphorically, biologically, truly younger, because their time moved more slowly. And it's not just theory. We've seen this effect on a small scale in labs and in orbit. We've measured it in particle accelerators, where subatomic particles are spun up to incredible speeds. Normally, they decay in microseconds, but at near light speed, they last much longer. Time slows down for them, just as it would for us. The universe doesn't care if you're made of atoms or ideas, it applies the same rules to all motion. So here we are, floating in this vast, cold dark, with time ticking softly behind us. You and I are moving, turning gently in this fabric of space, and with every motion, time shifts just a little. It's not fixed, it's elastic, like a great cosmic metronome that adjusts to your rhythm. You walk slowly, it ticks fast. You rush ahead, it ticks slow. And if you ride the edge of light, it stops entirely. Now think about light again, not just the speed, but what it means. Light isn't just a way for us to see. It's the universe's ultimate speed limit. No signal, no particle, no object can go faster. It's like a built-in safeguard that keeps the laws of nature stable. If anything could move faster, it would cause chaos. Cause and effect would get scrambled. You could send messages into the past. Events might happen before their causes. The arrow of time would lose its meaning. But because nothing can outrun light, the universe remains orderly. Time flows in one direction. The past stays behind. The future stays ahead. And right now, you and I are suspended in between, gently riding the slope of time's river, watching it curve with every motion, every mass, every photon that passes by. Isn't that beautiful? The universe doesn't need clocks to keep time. Time is baked into the geometry of space itself. As you move, as you stretch or compress the space around you, time flows accordingly. And the closer you push toward light speed, the more that flow slows down, until time feels like it's holding its breath. But it never quite stops unless you are light. Only a photon gets to experience that perfect stillness. For light, there's no such thing as before or after. It simply is. Born in a star, ending in your eye, in one eternal instant. Let's float a little longer in that silence. You're still with me, floating calmly in the dark, not drifting randomly, but gliding along a path that curves with gravity and motion and time itself. Look ahead. A beam of light is passing us now, moving impossibly fast. But from the light's perspective, nothing is happening at all. No distance, no time. That's the strangest part. For light, the entire journey from one galaxy to another takes zero time. No clocks tick. No moment ever begins or ends. To us, that light might take 1 billion years to cross the universe. But to the light, there's no journey, just a beginning and an end that touch. Now take a moment to really sit with that. It's not a metaphor, it's physics. At the speed of light, time completely halts. This isn't just something we made up in equations, it's baked into the fabric of the universe. Einstein figured that out over a century ago, and it's been tested again and again. We've measured time slowing down for fast-moving particles. We've built clocks that tick slower the higher you go, the faster you move, the deeper into gravity you fall. Time is not a rigid grid. It's soft, responsive, alive in a way. So when we ask, why does time slow down at light speed? We're really asking, what is time in the first place? And to answer that, we have to keep moving. You and I are leaving the comfortable zone of everyday experience now. Earth's rhythms, seconds, hours, orbits are falling behind us. Ahead, We're chasing the rules of the cosmos, where time is tied to motion itself. Let's turn toward a galaxy now, a spiral so wide it would take a beam of light 100,000 years to cross it. That's 100,000 years from our point of view. But to something moving faster and faster near the speed of light, those years would shrink. Time would compress. A ship moving close to light speed might cross the whole galaxy in a matter of hours, from the traveler's perspective. To them, everything outside would seem to blur, to rush past. But they wouldn't feel anything strange at all. Their heartbeat, their breathing, their thoughts all normal. Only when they returned and saw how much time had passed outside would the difference become shockingly clear. This is the power of relativity. It's not just that time slows, it's that time becomes relative to your motion. There is no single master clock ticking for the entire universe. Every point, every object, every person has their own timeline, and as you move faster, your path through time bends. It's not magic, it's geometry, just not the flat kind we're used to on paper. It's the geometry of space-time. Reach out now and imagine tracing that curve with your fingers. Space and time blend here. They're not separate. They're one thing, a four-dimensional shape that you and I move through. Most of us travel through time at full speed and stay still in space. But the faster you go through space, the slower you go through time. That's the trade. One direction borrows from the other. It's like you only get so much motion to spend, and the more you spend on moving through space, the less you have left for moving through time. This is why, as your speed increases toward the speed of light, your movement through time slows. You're spending everything on space, and at light speed, you spend it all. Nothing is left for time. The clock inside you stops ticking, but here's the twist. Only someone outside your frame of motion sees this happen. From your perspective, nothing changes. That's the great beauty of relativity. Everyone always feels normal inside their own experience. Now, let's move through a field of high-energy particles near a black hole's accretion disk. These particles are being whipped around at speeds incredibly close to light. We've seen this with telescopes, material moving so fast that time for those particles slows dramatically. They decay more slowly. They last longer. Their life stretches because their clocks are ticking slower. We're not guessing. We observe it. And every observation reinforces the idea that time and speed are intimately linked. Even astronauts experience this. When people live on the International Space Station, orbiting Earth at over 17.0 miles per hour, their time passes just a tiny bit slower than ours. It's only milliseconds over months, but it's real. They age more slowly than we do. Not enough to notice, but enough to measure. Over decades or centuries of high-speed space travel, it would add up. And that brings us to a beautiful concept: time travel to the future. Not with a machine, not through fantasy, but through velocity. If you had the technology to accelerate to near light speed and back, you could leap into the future, leave Earth, travel for a year at nearly light speed, return, and find that centuries have passed on Earth. This is time travel, built right into the way the universe works, not through tricks, but through speed. Of course, you can't do the reverse. You can't go back. That's not how the laws bend. Light speed lets you move forward through time at different rates, but never backward. It's a one-way road, with curves and shortcuts, but always forward, and that makes it even more precious. Every tick, every breath, every step forward is unrepeatable. The arrow of time is sacred, and it's shaped by your motion, your gravity, your place in the universe. Now we're gliding past a region where interstellar dust swirls slowly around ancient stars. These are some of the oldest suns in the galaxy, born when the universe was still young and hot. Their light has taken billions of years to reach us, and yet, that light is still moving at the same speed as it did when it left. No matter how far it's traveled, no matter how long it's been racing through expanding space, it has never changed its pace. That's another clue. Light doesn't age. It doesn't wear out. It just keeps going, untouched by time, because it never experiences time at all. It's a messenger, frozen in motion. And the moment you try to chase it, the universe resists, not by slowing the light, but by slowing you. And here we are, still chasing, gently, patiently, watching the stars drift, the galaxies stretch, and time bend beneath our feet. Every second we move faster, the clocks around us seem to speed up, but our own rhythm slows. We are becoming like light slipping forward in space, stretching behind in time. And even though we'll never quite reach that final speed, we're always able to approach it. Now take a slow breath. Let it out. We're gliding through the emptiest stretches of intergalactic space, the kind of dark that's deeper than night. But up ahead, something flickers faint, fast, and beautifully strange. A particle born in the heart of a supernova, maybe billions of years ago, is still traveling. Still moving at nearly the speed of light. Its journey is quiet and incredibly long, but from its point of view, no time has passed at all. It's as if it was created and arrived at its destination in the same breathless instant. That's the weird magic of near light speed travel. From the particle's perspective, the cosmos itself has shrunk. The vast gulf between galaxies collapses. Time dilates. And its trip, though millions of light years long to us, feels immediate to it. You and I, floating beside that particle now, are still bound by regular time, but the closer we approach its velocity, the more the universe bends around us. If we could accelerate just a little more, clocks on Earth would tick faster and faster from our point of view. Cities would rise and crumble in what feels like a blink. Civilizations would pass. Stars would flare and fade. But for us, time would be crawling as if we were moving through syrup instead of space. Einstein showed us this, not through intuition, but through math and logic. Special relativity. It tells us that time and space are linked, braided together in something called space-time. And that braid shifts depending on how fast you move. At everyday speeds, the effect is tiny, negligible. But as you edge toward the speed of light, the fabric itself stretches. A second for you might become a century for someone standing still. And it's not just about moving fast in space. Gravity bends time too. Let's turn slightly now and drift toward a dense object, a neutron star. From a distance, it looks peaceful, just a faint white glow, like a pearl against black velvet. But get closer, and the facts become dizzying. A neutron star is incredibly heavy, more massive than our sun, but only about 20 kilometers wide. That's like stuffing Mount Everest into the size of a city. The gravity here is so strong it crushes atoms, squeezing protons and electrons into neutrons. If you stood on its surface, not that you could time for, you would tick more slowly than it would for someone farther away. Not because you're moving fast, but because you're deeper in gravity's grip. This is called gravitational time dilation. We've measured it too. Atomic clocks flown on airplanes or placed at the tops of tall buildings run slightly faster than ones at sea level. The higher you are, and the farther you are from Earth's center of mass, the faster time flows. It's a small difference, but real. The GPS in your phone, right now, depends on accounting for this. Satellites high above Earth have to adjust for the fact that their clocks run a little faster than those on the ground. If we didn't correct for it, GPS directions would drift by kilometers every day. Now tilt your head and imagine, what would happen if we went deeper than a neutron star, all the way to a black hole? Black holes are extreme. Gravity there is so strong that the escape velocity, the speed needed to break free, exceeds the speed of light. Nothing can escape, not even photons. That's why they look black. Not because they're empty, but because light itself can't break free of their edges. That edge is called the event horizon. And here's where it gets even stranger. From a distance, it seems like time stops at the horizon. If you watch someone fall into a black hole, their movements would appear to freeze, their light stretched and redshifted into nothing. But for them, time feels normal. They cross the horizon in finite time, unaware that the outside universe is racing forward. If you hovered just above the horizon, not inside, just close your time would stretch too. A second for you might be thousands of years for someone watching from far away. You'd be skipping through centuries, your body aging slowly while the galaxy spins on. It's all part of how gravity and speed shape our experience of time. Now glance upward, a gentle shower of cosmic rays is passing through us. They come from all over, distant galaxies, exploded stars, ancient collisions. Some travel just under light speed, so fast that their own clocks barely tick. They're like messengers from the earliest days of the universe, carrying history inside their motion. And remember, the faster they go, the less time they experience. Not just figuratively, literally. If you were traveling alongside one of those particles, you could traverse an entire galaxy in what feels like moments. while the rest of the universe aged, you'd barely notice the passing seconds. That's what time dilation gives you, a way to move forward in time without aging, along with the world around you, a way to, in a sense, cheat the clock. Some physicists have even imagined distant future civilizations using this traveling close to light speed, not to get somewhere fast, but to leap forward in time. You could launch a ship, travel for a few years from your perspective, and return to a solar system that's thousands or millions of years older. Not because you warped space, but because time simply flowed differently for you. And again, this isn't science fiction. It's baked into the equations that describe our reality. It's been tested in particle accelerators, in orbit, with atomic clocks, with muons and GPS and distant starlight. Every experiment confirms it. Time doesn't move the same for everyone. It's woven into motion and gravity and space. You and I, we're part of that fabric too. Let's glide just a little farther now. The stars around us blur into streaks. Distant quasars spin lazily on the edges of the visible universe. And behind it all is the same truth. The closer we come to light speed, the more time stretches. It slows, it thins, and at light speed itself, it stops completely. And that's the mystery that still sits at the center of everything. Let's keep drifting together. There's more to feel, more to wonder at, and so many questions still left in the silence. So here we are, floating through a pocket of intergalactic space where galaxies are little more than distant smudges of light, and the silence is total. You can stretch your hand out, there's nothing to touch, not even dust, but there's a kind of stillness here that hums with meaning. This is the perfect place to think about something strange. To anything traveling at the speed of light, time doesn't exist at all. That's a bold thing to say, but light photons experience no passage of time. From the moment a photon is emitted, say from the surface of a star, until the moment it hits your eye, or a telescope lens, or a piece of glass a billion years later, no time passes for it. From its point of view, it left and arrived in the same moment. It doesn't age, it doesn't change, and it doesn't experience distance the way we do. It's as if the entire stretch of space it crossed from the edge of a galaxy to the back of your retina collapsed into nothing. The space and time between its origin and its destination simply didn't exist. Let that sink in. It's not just about going fast. It's about the fact that at light speed, space-time behaves differently. Massless particles like photons don't experience time because, in a way, they're not in time. They move through space-time on a path called a null geodesic, which sounds fancy, but really just means that they exist right on the line between space and time. Neither one dominates. They live on the edge of both. And you and I, we're still made of matter, still resting firmly in time. But the closer we approach the speed of light, the more our experience starts to resemble that of a photon. Time slows down for us. Distances shrink in the direction of travel. And eventually, if we could somehow reach the speed of light, which we can't, our journey would collapse into a kind of instantaneous state. No time, no space, just arrival. But remember, that's impossible for us. We have mass, and mass can't reach light speed. It would take infinite energy, and there's just not enough fuel in the whole cosmos to push us there. Still, we can come close. Particle accelerators on Earth have done just that. In places like CERN, scientists hurl tiny particles around at speeds, just a whisper below light speed. And those particles behave exactly as Einstein predicted. Their clocks slow, their lifespans stretch. Muons, particles that decay in microseconds, live thousands of times longer simply because they're moving fast. We've observed this over and over. Time dilation isn't a theory anymore. It's a tool. We use it every day in GPS satellites, in planning high-energy physics experiments, in understanding the behavior of stars orbiting near black holes. And it goes deeper still. Let's float toward a binary star system now, two stars locked in orbit around one another. One of them is a regular star, like the Sun, the other, a pulsar, a type of neutron star that spins hundreds of times per second, flashing beams of radio waves into space like a cosmic lighthouse. These systems are fascinating not just because they're beautiful, but because they bend time around them. The pulsar's incredible mass compresses space-time so tightly that the nearby star's orbit wobbles not randomly, but in a predictable way. This effect is called relativistic precession, and it's another direct sign that time itself bends around massive objects. By studying these wobbles, scientists have confirmed general relativity to extraordinary precision. Even the shape of light changes when it passes near a heavy object. It bends not because light has weight, but because space-time is curved. Light simply follows the path laid out for it. In 1919, astronomers watched starlight bend around the sun during a solar eclipse, and the world saw for the first time that gravity doesn't just pull on things, it warps reality. Let's turn now and drift past a galaxy cluster. Look at the space between the galaxies. Empty, right? But it's not really. It's filled with something strange, dark matter. We can't see it, but it makes up most of the mass in the universe, and its gravity also distorts space-time. Behind this cluster, the light from more distant galaxies is bent into rings and arcs, as if we're looking through a warped window. This effect is called gravitational lensing, and it's more than just pretty. It's proof that space-time bends not just near stars, but across vast cosmic distances. And again, wherever space-time bends, time changes. Let's ease in closer to that gravitational lens now. You'll see how the shape of distant light changes, but if we had a clock floating with us, it would tick more slowly than one floating in emptier space. Just by being in this slightly deeper gravity well, time is altered, gently, relentlessly, invisibly. You see, time isn't some universal drumbeat ticking through the cosmos. It's flexible, local. If you move differently, or exist in a place where gravity is stronger, your time flows at a different rate than mine. That's hard to accept, isn't it? We feel time as something constant. We live by it, sleep by it, age by it. But the universe doesn't care about our clocks. It lets time bend and stretch and stall, depending on motion and mass. Even now, as we coast farther away from anything recognizable past the halos of galaxies and the last glimmers of starlight, time still has shape. There are places where it moves slower, others where it races ahead, and still others for particles riding beams of light, where it doesn't move at all. Let's stay here for a moment and breathe that in. If you held a stopwatch at your side and I floated away from you at 99% of light speed, you'd see my seconds stretch out. To you, I'd seem to move in slow motion. But if I looked at my own watch, everything would feel normal. I'd be aging at my regular pace. It's not an illusion, it's a fundamental difference in how time behaves depending on the observer. And it's mutual. From my point of view, your clock would be the one running slow. Both perspectives are valid. That's the beauty and strangeness of relativity. There's no absolute now that stretches across the cosmos. Every object carries its own clock, its own slice of reality, ticking at its own rhythm. That rhythm depends on speed, on mass, on proximity to black holes or stars or nothing at all. And the closer you push toward light speed, the slower your internal clock moves compared to the rest of the universe. That's why, if you flew near light speed for a year, your year you could return home to find centuries had passed. The math is solid, the physics is real, and the possibilities, while difficult, are awe-inspiring. We're not just floating through space tonight. We're gliding through time's fabric, peeling back its folds, feeling how motion reshapes reality itself. We're still gliding forward, you and I, side by side in a kind of cosmic hush that's hard to put into words. You might notice how the stars are thinning out behind us. We've drifted so far now that whole galaxies have become faint pinpricks, but there's still so much ahead. Especially if we keep thinking about what time really is and what happens to it when you travel close to the speed of light. Let me ask you to do something strange. Imagine you're made entirely of light. You don't have bones or breath anymore. No weight, no temperature, just a flash of energy. In that form, time doesn't touch you. You could be sent across the entire galaxy, and to you the trip would be instantaneous. No waiting, no aging. You'd leave one star and arrive at another in the same instant, even if the distance between them was hundreds of thousands of light years. But of course, we're not made of light. We have mass, and that changes everything. Because once you have mass, time has something to grab onto. It pulls on you gently, subtly, but always. Mass and motion are the twin forces that determine how fast your internal clock ticks, and both of them matter when you're talking about near-light speeds. The faster you move, the more time slows down for you. This isn't just a curious side effect. It's a fundamental rule of the universe. If we could build a spaceship one strong enough to accelerate constantly for years, we could ride it to speeds just under the speed of light. And while it might feel like only a few years passed for us on board, centuries, even millennia, could pass outside. This idea is known as the twin paradox. Picture it like this. Two twins are born at the same time. One stays on Earth. The other boards a spaceship, accelerates to near light speed, flies away for a while, then turns around and comes back. When the traveler returns, they find that their twin has aged decades more than they have. To the traveler, it felt like a short trip, but to the one who stayed behind, it was a lifetime. This isn't science fiction, we've seen it happen on smaller scales. Remember those muons I mentioned earlier? They're born high in Earth's atmosphere when cosmic rays strike air molecules. At rest, they decay quickly in microseconds, but because they're moving so fast, we can detect them on the surface. They live longer than they should. Not because their biology has changed, but because their time is running slow compared to ours. That's what high speed does. It stretches time out like soft taffy. From the outside, everything inside the fast-moving frame appears slower, and the effect doesn't start. Suddenly, it's gradual. At 30,000 kilometers per hour, time only slows by a tiny fraction. But once you approach 99% of light speed, those differences become profound. And speed isn't the only way time warps. Gravity, too, slows time down. Let's hover near a dense planet now, maybe a super-Earth, twice as massive as our home. Even here, just standing closer to something massive makes your time tick more slowly. If you stood on its surface and I floated 100 kilometers above, our clocks would drift apart, mine ticking faster, yours ticking slower. This has been proven over and over. In fact, the GPS satellites orbiting Earth have to account for both motion and gravity. They move fast, which makes their time run slower. But they're also farther from Earth's gravity, which makes their time run faster. Engineers have to balance both effects to keep your location accurate. Without corrections for time dilation, GPS would drift by kilometers every day. That's the real magic here. This isn't just theory, it's technology. Time isn't fixed. It's fluid, local, alive. The universe lets it bend and stretch depending on where you are and how you move. And nowhere is that more dramatic than near a black hole. Let's glide closer to one now. You might see it ahead, not a hole, exactly, but a black sphere surrounded by glowing arcs of falling gas. It's the remains of a star many times larger than our sun. When it collapsed, it didn't just crush its matter into an infinitely small point, it crushed time too. Around every black hole is a boundary called the event horizon. Cross it, and you can't come back. But even before you reach it, time gets strange. From our point of view, watching someone fall in, they never quite reach the edge. They just slow down, freeze, and fade. Their light becomes redder, stretched to longer and longer wavelengths. Eventually, they vanish. But from the point of view of the falling traveler, time feels normal. They don't notice anything special when they cross the horizon. No explosion, no pain. Just a silent crossing into a place where the rules are no longer the same. What's really happening is that gravity is distorting space-time so much that the very shape of time itself is bent downward. The closer you are to the black hole, the more time slows relative to the outside world. At the edge, it slows infinitely, and inside, well, we don't fully know. The laws of physics as we know them break down, but the math tells us that time and space switch roles. Inside the event horizon, you don't fall toward the center in space. You fall toward it in time. You can't avoid it, any more than you can avoid tomorrow. This tells us something profound. Time isn't some passive backdrop where events happen. It's part of the landscape. It curves, it twists, it stretches. And when you move through space, especially at high speeds, you also move through time in a different way. Let's drift gently away from the black hole now. The air, if there were any, would be still. The stars beyond are slightly distorted, their light curved by the black hole's gravity. But out here, we're safe again. Time flows more normally. Still, the lesson remains. If you want to slow time, go faster. Move close to something massive, or both. That's what astronauts feel just slightly when orbiting Earth. Their motion slows time, but being higher up in weaker gravity speeds it up. For those aboard the International Space Station, these effects nearly cancel each other out. But for satellites farther out, it matters more. And for future missions to Mars, or Europa, or beyond, understanding how time changes will be crucial. And yet, time dilation is only the beginning. There's another piece of this puzzle, something strange, elegant, and central to everything we've seen so far, the idea that time and space are part of a single fabric, space-time. So, let's settle deeper into this thought that space and time are not separate. They're intertwined. Every movement through space is a movement through time, and every bend in one curves the other. We live not in a static backdrop, but in a shifting, pliable fabric called space-time. And this fabric isn't smooth, it ripples, it stretches, it even trembles slightly from distant events. If something massive moves like a pair of black holes colliding, it doesn't just create waves in space. It sends out ripples in space-time itself. These are called gravitational waves, and we've detected them. Real echoes from events billions of light years away, tickling the fabric of reality just enough for our instruments to feel the shiver. Let that settle in for a second. The universe has a texture, a feel. It reacts when mass moves, and we can sense it. That's because everything in space-time is connected through motion, gravity, and yes, time. Now here's where things get even more fascinating. If you were to shine a light in a dark room, no matter how fast you move, that light will always appear to travel away from you at the same speed, 300,000 kilometers per second. Always. That's one of the most puzzling, elegant facts of the cosmos, and it's the reason time bends at high speed in the first place. Because if light's speed never changes even when you move toward it or away, then something else has to give, and what gives is time. As you speed up, your own clock ticks slower, so that the speed of light stays the same for you, and for everyone else too. This is the heart of Einstein's theory of relativity. He realized that space and time aren't absolute. They're relative to motion, to gravity, to the observer. And the speed of light is the great constant that ties everything together. It's the universal limit. Nothing with mass can reach it, because doing so would require infinite energy. So we can get close, but never touch it. And as we approach that limit, time slows more and more, approaching zero. This is why light itself doesn't experience time. A photon, born in the heart of a star, can travel for billions of years to reach your eye, but for that photon, no time has passed. Its journey, from emission to arrival, was instant. It never aged, because in its own frame, the beginning and end are the same point. That's hard to picture, but try this. Imagine light like a stretched rubber band, snapped from one end of the cosmos to the other. We see the journey unfold across years or centuries. But for the light itself, it was never a journey. It just is. Now, apply that same idea to ourselves. If we were somehow able to accelerate and coast at 99.9% of light speed, a trip to a distant galaxy might take us only a few years on board. But when we returned, we might find that millions of years had passed back home. The faster you go, the slower your time runs compared to everyone else's. This is called time dilation, and it's not a theory, it's observed. Muons live longer. GPS satellites need constant adjustment. Atomic clocks flown on jets tick at different rates than those on the ground, all because time is flexible, not broken, just curved. And this matters not just for space travel, but for understanding the age of the universe itself, because time doesn't tick the same everywhere. In strong gravity, time passes more slowly. That means when we look at ancient stars in faraway galaxies, we're not just seeing them across space, we're seeing them across different timelines. The deeper into the past we peer, the more the universe's structure distorts our sense of now. Let's pause for a moment and hover near a quasar, a brilliant beam of energy powered by a black hole at the center of a young galaxy. Light from this object has been traveling for over 13 billion years. But in the time that it took that light to reach us, countless generations of stars have come and gone. Civilizations may have risen and faded on planets we'll never see. Now imagine if we were moving toward that quasar at near light speed. Its light would seem blue-shifted, crammed into a tighter, more intense signal. Its pulses would arrive faster. Time, from our perspective, would seem to speed up in its direction. That's another effect of high-speed travel. Not only does your time slow, but incoming signals appear accelerated. This is how time, motion, and space all weave together into a living tapestry, one where your direction of movement changes what you see, hear, and feel. It also means that every observer has their own version of now. Your present moment is different from someone else's if they're moving fast enough or deep in a gravity well. There's no universal clock ticking for the cosmos. There are only local clocks, all valid, all relative. And yet, we make sense of it. We live inside it. Our heartbeat, our breath, our aging, all of it shaped by how we move and where we stand in this curved, flexible space. Now let's glide past a neutron star. You'll see it spinning hundreds of times per second. It's small, only about 20 kilometers across, but it has more mass than our sun. That's why its gravity is so intense. If you stood near its surface, if such a thing were even possible, time would crawl compared to Earth. A single second for you might equal days or weeks for someone watching from orbit. This is why neutron stars and black holes are such powerful laboratories for studying time itself. They warp space-time so sharply that clocks near them behave in ways we can barely simulate. And yet, thanks to pulsars, neutron stars that flash regular beams of radiation, we can measure their rhythms with astonishing accuracy, sometimes to within a few billionths of a second. That precision lets us study how time flows in extreme environments and confirms again and again that Einstein was right. But there's still so much we don't know. At the smallest scales in the quantum world, time behaves even more strangely. Particles can exist in multiple states until observed. Some processes appear to go forward or backward, and time, which seems smooth to us, might be granular, made of tiny units we just can't detect yet. That's part of the great mystery still waiting for us out here, how gravity, motion, and quantum mechanics all come together to shape time at every scale. Picture us now, gliding gently near the event horizon of a black hole. This is one of the most extreme environments in the universe, where the fabric of space-time is pulled so tightly that it folds inward. If we were to hover just outside the horizon, that invisible boundary beyond which nothing returns, we'd feel time slow down in a very real way. From your point of view, everything feels normal. Your heart beats, your thoughts drift, your breath moves at its own quiet rhythm. But to someone far away, watching you from a safe distance, it would seem like you're moving slower, much slower. In fact, if they watched you fall toward the black hole, you'd appear to freeze right at the edge, never quite crossing over. That's how strong the gravitational time dilation is here. For you, seconds pass, but for the outside universe, centuries might go by. And this isn't just theory, we've actually measured time differences using satellites around Earth. One of the first tests of general relativity involved placing precise atomic clocks at different altitudes. The clock closer to Earth, deeper in gravity, ticked slower than the one higher up. Even just a few hundred kilometers can make a measurable difference. Now scale that up to a black hole, where gravity is billions of times stronger, and time becomes something flexible, bendable, stretched. Here's the key idea again. Time doesn't flow the same everywhere. It flows relative to gravity and to motion. The closer you are to something massive, the slower time moves for you, compared to someone farther away. The faster you move through space, the slower your clock ticks, compared to someone at rest. That's why astronauts in orbit age ever so slightly less than people on Earth. The effect is tiny, just milliseconds, but it's real. Our GPS systems actually need to correct for it constantly. The satellites up there are both moving fast and sitting higher in Earth's gravitational field. If we didn't account for time dilation, GPS would be off by several kilometers each day. But let's go deeper. Imagine we could ride alongside a beam of light, just behind it. Not at the speed of light, we can't reach that, but really close. At 99.999% of light speed, the world around us would start to distort. Stars ahead would seem to bunch up, their light squeezed into brighter, bluer wavelengths. Behind us, light would stretch and redden, fading out, and the faster we go, the more dramatic this effect becomes. Eventually, the entire universe seems to collapse into a bright oval in front of us, with nothing visible behind. That's relativity at work. The way you move shapes what you see. It shapes what you feel. And most importantly, it shapes how you experience time. This is why time slows at high speed, because in order to keep the laws of physics, especially the speed of light, consistent for every observer, nature has to adjust something, and it adjusts time. It bends it. It lets you age more slowly, tick more gently, move through fewer moments than those standing still. You might not feel it, but the difference is there. Now let's glide outward again, away from that black hole. Let's float in the calmer regions of deep space. The light here is older, fainter, but it still carries echoes of the universe's earliest moments. Some of the photons brushing past us were released just 380,000 years after the Big Bang. We call this the cosmic microwave background, the afterglow of creation. It's everywhere, uniform, gentle, like a whisper left behind by the moment the universe cooled enough for light to finally travel freely. And even here, time has left fingerprints. The tiny temperature differences we measure in this background light show us how gravity slowly pulled matter together, forming galaxies, stars, planets, and us. These fluctuations tell a story about how the early universe wasn't quite uniform, and those slight imbalances are what led to structure, to shape, to time as we know it. Let's reach back even further, as far as physics can describe, back to the first moments after the Big Bang. Time, as we understand it, began here. Before that moment, it's not just that we don't know what came before, it's that the concept of before may not even apply. Time may have unfolded from that initial expansion, woven into space itself. One doesn't exist without the other. And in that fraction of a second, everything changed. The universe inflated rapidly, expanding faster than the speed of light, not the stuff inside it, but space itself stretching. In those early moments, particles were born, forces emerged, and time began ticking forward, and it's been ticking ever since, but again, not evenly. Gravity, motion, and matter have shaped the rhythm of time everywhere. Imagine now that we could somehow fold space, not travel through it in the usual way, but bend it. If that were possible, then maybe we could connect distant points in an instant. This idea of wormholes or shortcuts through space-time is a real solution to Einstein's equations. We haven't found one yet, but on paper, they could exist. And if they do, then time gets even stranger, because moving through a wormhole could allow one end to be in a different time than the other. Travel far and fast enough, and you might loop back into the past or forward into a future no one else has reached. This is all part of why light speed is such a profound boundary. It's not just a speed limit, it's a horizon, a place where our understanding of time begins to unravel. The closer we get, the more everything stretches and bends and twists, and that's what makes it beautiful, because it tells us that time is not a constant march. It's a flowing, shifting thing, shaped by the universe itself. We'll keep drifting, you and I, still floating through this quiet cosmic sea, still watching time bend around stars and flow differently in the shadows of massive things, still listening for echoes from faraway events and tracing the curves in space-time that tell us where everything's been and where it's going next. Out here, you'll notice something subtle but powerful. We're far from any stars or planets, and yet gravity still exists. Not in the dramatic way we feel near a planet's pull, but in quiet curves, like soft indentations in space-time. You see, gravity doesn't turn off, it just fades gently with distance. And even the smallest tug has the power to bend time, just a little. This means that time, no matter where you go, is never entirely flat. Imagine you're floating perfectly still, miles above a planet, where gravity is faint, and then slowly, you drift downward. As you descend, you'd be entering denser gravity, and as you do, your time would stretch ever so slightly slower. You wouldn't notice it, but the deeper you go, the more your seconds drift apart from the seconds of someone higher up. It's almost poetic, time slowing, softening, the closer you fall toward the heart of gravity. This is called gravitational time dilation. It happens all around us. Even between your head and your feet are closer to Earth's center, so time there ticks just a hair more slowly than at the top of your head. It's an unimaginably small difference, but it's real. That's how sensitive time is. It responds to the slightest curve of gravity, to the faintest motion. It's not an independent force ticking away in the background. It's part of the living geometry of the universe. Now, think back to that beam of light. When we try to go faster, when we accelerate, we aren't just speeding through space. We're changing our trajectory through space-time itself. The faster we go, the more time must slow for us, to preserve that constant speed of light for all observers. And here's something remarkable. This slowing of time isn't just a side effect. It's a necessary part of how reality stays consistent. Because without it, light's speed wouldn't be the same for everyone, and that would break the rules that make physics work. So nature bends time instead. It chooses the smoothest possible path. That's why we say, Light travels along the straightest line in space-time, a geodesic, but in curved space, that line itself curves, and in this curvature, time gets involved. Now let's get closer again, deeper into speed. As we move faster, our mass, our resistance to acceleration increases. This is relativistic mass. The closer we get to light speed, the heavier we effectively become. It's not that we gain more stuff, but that the energy required to keep accelerating grows. At 99% of light speed, you're moving incredibly fast, but doubling your speed again requires almost twice the energy. At 99.9%, even more. And to reach full light speed, that would take infinite energy, infinite effort. That's why it's unreachable for anything with mass. But photons, light particles, have no mass, so they're not slowed down by inertia. They always move at light speed. They don't experience time. They don't age. For them, there's no before and after. Just emission and arrival. And now we're brushing against something deeper, the idea that time might not be a universal river flowing in one direction for all things. Instead, time could be like a slope on the surface of a hill, a direction shaped by gravity and motion, unique to every traveler. Every clock, every person, every spaceship, every particle has its own slope through space-time, its own direction, its own rhythm. Let's reach toward a white dwarf star. These are the remnants of sun-like stars that have burned through their fuel and collapsed inward. What's left is a dense, glowing ember about the size of Earth, but with a mass nearly as great as the Sun. That means incredible gravity. Time near its surface ticks measurably slower than time in open space. If we left a probe in orbit and waited, its clock would drift slightly behind ours. We'd see its seconds stretch out like soft taffy, not enough to notice minute to minute, but enough that over years, the gap would grow. Now multiply that across centuries, across billions of years. These little differences accumulate. Time, in one place, becomes history in another. And here's a curious thought. There are places in the universe where time has effectively stopped, at least from our point of view. Inside a black hole's event horizon, time is so warped that from the outside, nothing ever seems to cross the boundary. But for the object falling in, time feels normal. This is what relativity shows us, not just that time can be different, but that different experiences of time can both be true. It's humbling, isn't it? That we live in a universe where reality depends on where you stand, how fast you move, and how close you are to gravity. There's no one version of the truth, only countless valid perspectives, all stitched together by space-time. Now, let's hover beside a galaxy cluster. These are some of the largest structures in the universe, thousands of galaxies bound together by gravity. The space between them is not empty. It's filled with hot gas, dark matter, and light that's been traveling for billions of years. As light from distant galaxies passes through this cluster, the gravity bends its path, an effect called gravitational lensing. It stretches and magnifies background galaxies, letting us see deeper into the cosmos than we otherwise could. But it also affects time. Light passing through intense gravity loses energy redshifts. Its frequency changes, not because it's slowing down, but because it has to climb out of a gravitational well. This shift in frequency reflects a shift in time. It's subtle, elegant, a sign that gravity and time are always in quiet conversation. Every photon we catch from deep space is a time traveler. It left home long before Earth even formed. It may have passed near stars, through clouds of gas, around dark matter. And all along its journey, its time has been shaped by what it moved near. When we observe these photons, we're not just seeing across space, we're feeling across time, bent and stretched by gravity's invisible hands. You might not feel it, but we're part of that same flow. Our own time is shaped by Earth's spin, by the moon's pull, by the orbit around the sun. It's shaped by the mass of the galaxy we're spiraling through. Even now, as we drift together in this thought, we're feeling time a little differently than we would elsewhere, because to understand time is to understand the landscape we move through. And there's still more. We haven't even touched on entropy, the reason we remember the past but not the future, the arrow that gives time its direction. But for now, let's stay here, floating gently above this galaxy cluster, where time moves just a hair slower than in empty space. Let the stars drift around us like snow in slow motion. Now tilt your attention towards something ancient. There, ahead of us, is a neutron star. It looks small from a distance, just about 20 kilometers across, but don't let that fool you. It's heavier than our sun, packed into a space no bigger than a city. Imagine a single teaspoon of that star would weigh as much as a mountain. The gravity here is staggering, thousands of times stronger than Earth's. And here, time crawls. If you were to hover just above its crust, time for you would pass far more slowly than for someone watching from afar. A single hour here might feel like days outside. That's not science fiction, that's a measured fact. The intense warping of space-time around this object makes it one of nature's most dramatic, time-slowing machines. But despite the extremes, everything still works. Light escapes, particles spin, and the neutron star's own pulses keep perfect time with their surroundings. These neutron stars often spin hundreds of times per second, some up to 700 rotations every second, and we call them pulsars when their magnetic beams sweep past Earth like a lighthouse. They're some of the most precise clocks in the universe. In fact, scientists use them to measure galactic time and to detect tiny ripples in space-time called gravitational waves. Their regular pulses let us sense disturbances caused by things like black hole collisions billions of light years away. Imagine that time rippling outward, reaching us across the galaxy, carrying the echo of massive events long gone. And that brings us to something subtle but profound. Time isn't just warped by speed and gravity. It can ripple. When two massive objects spiral into each other, like black holes or neutron stars, their merger sends out waves through space-time itself. These gravitational waves stretch and squeeze everything they pass through. We've built detectors on Earth sensitive enough to feel those waves, stretching a laser beam by less than the width of a proton. And we've caught them. We've heard space-time ring. And in those rings, we hear time itself whispering across the cosmos. Now look around this space we're in. This quiet ocean between stars is still alive with motion. Galaxies spin, stars orbit, clouds drift and collapse, and all of it shapes time. Even now, here in this gentle corridor of the Milky Way, we're orbiting the galaxy's center at about 200,000 kilometers per hour. Every 230 million years we complete a full lap. We've done that maybe 20 times since Earth formed, and during every lap, time bends, not only because of the galaxy's mass, but because of our motion through it. Now lean a little closer toward our own solar system. Out here, on the outskirts, you'd see Voyager 1 and Voyager 2, human-made spacecraft still traveling decades after launch. They carry with them golden records, etched with messages from Earth, and they've now reached interstellar space. But their clocks? They tick just a little differently than ours, thanks to their distance, their speed, and the sunlight they no longer feel. They are, in a way, experiencing their own version of time. And what about time for Earth itself? Our planet doesn't spin at a constant rate. Over centuries, it's been slowing tidal forces from the moon stretch Earth slightly, causing friction. We've had to add leap seconds to keep atomic clocks in sync with Earth's rotation. Even this shows us how time, on a planet-wide scale, isn't fixed. It shifts, it drifts, it changes, just like we do. And now, reach out, feel the sunlight on your hands. That light left the sun 8 minutes ago, which means in a way, you're always seeing the sun as it was, not as it is. You're always looking slightly into the past, and that applies to everything. Light from Jupiter takes about 40 minutes to reach us. From Pluto, about 5 hours. From the nearest star, 4 years. From the center of our galaxy, over 25,000 years. And from the most distant galaxies, over 13 billion years. That's what makes space such a perfect place to study time. Every direction is a view into the past, every photon a time capsule, and because light has a limit, we can only see as far as time allows. The visible universe is bounded by the cosmic horizon, about 46 billion light-years in every direction, not because space ends there, but because light from farther away hasn't had time to reach us yet. Now let's step into the mind-bending realm of relativity once more. Remember, time slows down at high speeds not just as a trick of perception, but as a fundamental reality. The faster you move, the more your experience of time differs. If you spent 10 years traveling near light speed, you might return to find that 50 years have passed for everyone else. This isn't science fiction, it's been confirmed using fast-moving particles. Muons, for example, decay in microseconds when at rest. But when they move close to light speed in particle accelerators, they last much longer, not because their decay slowed down, but because their clocks slowed down, their time stretched. We've seen this same effect on Earth with airplanes. Precision atomic clocks flown around the world have shown slight time dilation compared to clocks left on the ground. Again, the difference is tiny, but real. The faster you go, the slower you age. The deeper you sit in gravity, the slower your seconds fall. Time is flexible. Time listens to your path. And now we come to something even stranger, the concept of proper time. This is the time you feel personally, the duration along your specific path through space-time. Two travelers can take different routes through space and end up experiencing different amounts of time, even if they meet again at the same place. It's like a road trip, where one person takes the highway and another wins through mountain trails. They both reach the destination, but one took longer because the route through space-time was different. This is where the twin paradox comes from. If one twin travels near light speed, then returns home, they'll be younger than the one who stayed behind. It sounds impossible, but it's built into the way space-time works. Time and space are not separate. They're one fabric. Move through one, and you affect the other. And all of this, the slowing of time, the bending of paths, the stretching of seconds, it all flows from one simple truth. Light has a maximum speed. That's the rule the universe refuses to break. And so everything else must bend to protect it. You and I, we're part of this bending. Our atoms, our breath, our thoughts, even this very moment is a product of space-time's geometry. And as we float through this quiet dark, we're not outside of it, we're inside it. We are time, moving through itself. Now look, just ahead we're coming close to something beautiful and strange. It's a globular cluster, a sphere made of hundreds of thousands of stars packed tightly together, orbiting like a swarm around the center of our galaxy. These clusters are ancient, older than Earth, older than the Sun. Many of them are over 12 billion years old, which means they formed when the universe was still young and bright and filled with hydrogen mist. These stars have seen time unfold from its earliest moments. They've watched galaxies spin, merge, change, and they move together, bound by gravity into a kind of stellar hive. Let's drift right through the middle. See how tightly packed the stars are here? In some parts of the cluster, they're only 1 light year apart. That's 50 times closer than stars in our local region of space. And it means the gravitational fields here are overlapping and complex, creating a web of forces that subtly bend time. If you lived on a planet inside a globular cluster, time might move just a little differently than out in the open galaxy. Not by much, but enough to measure if you had a precise enough clock. That's one of the incredible things about time. It listens to gravity in tiny, quiet ways. Even Earth's own mass is enough to slow time down slightly for you, compared to someone high above in orbit. In fact, GPS satellites have to correct for time dilation constantly, both from the speed at which they move and the weaker gravity they experience compared to someone on Earth's surface. Without adjusting for relativity, GPS systems would drift by about 10 kilometers each day, and yet we use them to guide airplanes, phones, and ships. Every time you get directions from a map app, you're relying on Einstein's equations humming quietly in the background. Let's glide further now. We're heading towards something vast, a galaxy cluster. Look at how enormous this is. Thousands of galaxies bundled together by gravity, stretching across millions of light years. This isn't just a single system, it's a city of galaxies, and in the space between them is dark matter, invisible, but detectable through its gravitational pull. This dark matter is what keeps the cluster from flying apart. We can't see it directly, but we know it's there because of the way galaxies move. Now, here's where it gets wild. The gravity of the entire cluster bends light, not just nearby light, but light passing through from even more distant galaxies behind it. This is called gravitational lensing. The cluster acts like a cosmic magnifying glass, warping the background and distorting it like glass underwater. But it's not just the light that bends, time bends too. If you were to hang out on the edge of this massive cluster, your seconds would tick just a tiny bit slower than someone in deep intergalactic space. That's the power of mass. It doesn't just shape space, it carves valleys in time. Now let's shift toward motion again. Imagine you're riding a spaceship, sleek, silent, fast. You start slow, then build speed. 1,000 kilometers per hour, 10,000. 100,000, a million. As you approach the speed of light, something strange happens. Not outside the ship that still looks the same, but inside, your time slows. The closer you get to light speed, the slower your clock runs compared to the universe around you. You could travel for what feels like a week, and return to find centuries have passed outside. This is time dilation, one of the core effects of special relativity. But it's not just theory. We've measured it in particle accelerators. Tiny particles called muons, which normally live for about 2 microseconds, survive much longer when accelerated to near light speeds. They live because their time is stretched. And in their own frame, nothing has changed. It's the rest of the universe that seems to move faster. And here's something even deeper. If you were to somehow travel at the speed of light, which, to be clear, nothing with mass can ever do, your experience of time would stop entirely. That's right. From the perspective of a photon, the moment it leaves a star and the moment it hits your eye are the same moment. No time passes at all. It experiences the universe as flat, immediate, timeless. It's one of those things that's hard to wrap your head around, but it shows us just how strange and flexible time truly is. Even the temperature of the universe is part of this story. Right now, all of space is filled with a faint glow called the cosmic microwave background. It's the leftover heat from the Big Bang, stretched by expansion into cold, invisible radio waves. That radiation is only about 2.7 degrees above absolute zero, just a whisper of warmth. But it tells us how time began. It's a picture of the universe when it was only about 380 years old, glowing, smooth, and filled with potential. Reach out and feel that cold hum. It's been traveling for over 13 billion years just to reach us. And it too has been slowed not by gravity, but by the expansion of space itself. As the universe stretches, it also stretches time. That's why distant events look frozen in slow motion, like echoes that never quite fade. When we look far away, we're not just looking through distance. We're looking through time that's been slowed by the cosmos itself. And now, let's press onward again. Beyond the clusters, beyond the walls of galaxies, out into the void. These voids are vast, hundreds of millions of light years across, nearly empty of galaxies. But even here, time flows, smooth, quiet, undisturbed, the perfect place to reflect on what we've learned. Time is not a ticking clock. It's not a fixed river. It's a flexible fabric, shaped by energy and mass, bent by speed and gravity. And though we live our lives thinking of time as steady, it's anything but. You're doing great still with me, floating through this enormous, intricate universe, unraveling the secret curves of time together. I'm really glad you're here. Keep whatever quiet comfort you've got nearby, that cozy blanket, that cup of tea, or the gentle patter of rain if it's your kind of evening. We're still traveling, you and I, and we're getting deeper into the mystery. No rush, just steady, curious movement through the stars. Look, just off to your left you see that flickering beam sweeping slowly across space. That's a pulsar. It's the collapsed core of a massive star, a neutron star spinning incredibly fast and blasting out beams of radio waves. Some of them spin hundreds of times per second. They're so precise, in fact, that astronomers use them like cosmic lighthouses to keep track of time and location in deep space. But even their pulses aren't immune to time's flexibility. The stronger the gravity they sit in, the slower their ticking becomes compared to clocks far away. Now think about that for a second. Time ticks differently depending on where you are, how fast you're moving, or how close you are to massive objects. That means there is no universal now. The moment you're experiencing right this second might be the future or the past for someone else, far away, in another gravity well, or zipping past at a fraction of light speed. In the vast theater of space, time doesn't play fair, and that's part of what makes it beautiful. Let's drift closer to a neutron star. You can't see it well with your eyes, it's tiny, only about the size of a city, but its gravity is immense. A teaspoon of its material would weigh as much as Mount Everest. If you hover too close, your clock slows, light bends, tides stretch objects. But from a safe distance like this, it's a glowing, flickering reminder of what gravity does not just to space, but to time. It warps it, folds it, makes it run uneven, like a record slowing down at the edge. Now let's turn towards something even stranger. Just ahead, a black hole. It's quiet, dark. At first, It doesn't even look like anything, just a place where the stars go missing. But you'll notice how light from behind it curves around the edges, creating a glowing ring. That's gravitational lensing at work again. The black hole isn't pulling in light, it's curving, the very space light travels through. And time? Oh, time behaves differently here than anywhere else. As we hover near the event horizon, the edge of the black hole, look at your watch. Imagine it ticking slower and slower. To someone far away, your time almost stops. They'd watch you freeze in place, just hovering, never falling in. But from your perspective, everything feels normal. You'd drift in calmly, and the outside universe would rush by. Time would fly for them and crawl for you. That's how extreme gravity works. It doesn't just pull on things, it bends the whole story of how events unfold. And get this, black holes don't just bend time, they also store it. Information, actually. There's a whole field of study called black hole thermodynamics that deals with how information is preserved in these objects. Because in the end, physics tells us that information can't be destroyed. Not really. And somehow, the surface of a black hole, its event horizon, encodes everything that's ever fallen in, including the time that information existed. It's like a cosmic filing cabinet with no way to reach in. Let's pull back gently now. Don't worry, we're still outside the event horizon. Time is still flowing for us, even if a little slower. But keep that feeling in mind, that pause, that stretch, that strange slowing, because it tells us something deep about our universe. Time isn't fixed. It doesn't move the same for everyone. It stretches, warps, halts, and the closer you get to the speed of light or the edge of a black hole, the more you feel it. Now picture this. Imagine a spaceship heading toward the speed of light. From the pilot's point of view, the stars ahead start to blue shift their light, compressing into higher energies while the stars behind redden and fade. The outside universe appears to shrink into a tunnel, like a long hallway of flickering light. Inside the ship, everything feels normal. But from the outside, your clock is crawling. Someone watching you would say, they've nearly stopped. The faster you go, the more the universe sees your time freeze. And here's a twist from your point of view. You're not slowing at all. You're still experiencing seconds as seconds. It's the outside universe that's changing, rushing by in fast forward. This isn't just poetic, it's been proven in labs. Particles moving near light speed decay slower. Astronauts on the International Space Station age just a little less than we do on Earth by a few milliseconds, but still measurable. That's real, practical relativity in action. And the effects get bigger the faster you go. If you could fly at 99.99999% the speed of light, 1 year of your journey might equal thousands of years on Earth. You could travel to the edge of the galaxy in what feels like a week, only to return and find entire civilizations gone, mountains eroded, coastlines changed. That's what time dilation really means. It's not just slower clocks, it's changed realities. Two people moving at different speeds, or living in different gravity, will never agree on how long something took. Their time has genuinely flowed differently, and there's no right version, they're both correct for their frame of reference. Let's float out now, far beyond the Milky Way. We're out in deep intergalactic space, where the stars are dim and the void stretches endlessly. Here, time flows more evenly, there's little gravity to warp it, no massive objects to slow it down. But even here, light from distant galaxies is red-shifted. That's not because they're moving quickly through space, but because space itself is expanding. And as it expands, it stretches light. And stretching light means stretching time. So when we look at a galaxy 10 billion light-years away, we're not just seeing an old image. We're seeing an event that happened when the universe itself was smaller, denser, younger, and we're seeing it slowed, its flickers frozen in expansion. We'll stop here for just a moment. Float with me in this stillness. Think about how every star you see is a clock, every orbit a rhythm, every photon a traveler carrying time. The universe isn't just a stage where time plays out. It's an active participant, bending, flexing, whispering secrets through the silence. And time, for all its strangeness, is how we witness the unfolding of everything. So here we are, you and I, still drifting quietly through the fabric of space and time. We've been voyaging together across billions of years, through the rise and fall of stars, past glowing galaxies, into the slow hush of black holes and the strange stillness of the speed of light. You might be feeling a bit small right now, or maybe a bit timeless yourself. That's okay. That's kind of the point. Space has a way of doing that to us. But it's also comforting in a way, isn't it? To realize that no matter where or when we are, time is always with us, not as a ticking clock, but as a rhythm, a flow, a backdrop against which the universe plays out its luminous, quiet story. We felt what it's like to hover near a pulsar, to run our fingers along the fabric of warped time beside a black hole. We've imagined racing so fast that the universe slows to a crawl, while inside the ship, your heartbeat remains steady and warm. You've seen how time stretches, how it bends, how it gently disagrees with itself, depending on your speed or your place in the cosmos. And none of that was science fiction. It's all real, not just theoretical, but observed, measured, lived. GPS satellites account for time dilation every single day to give us accurate positions on Earth. Particle accelerators stretch the lifetimes of unstable particles just by pushing them close to light speed. Even a simple wristwatch runs a smidge differently on a mountaintop than it does by the sea, just because of gravity's slight grip. So the next time you glance at a clock, just remember it's not absolute. It's local, personal. A clock is not the same as time. It's a gentle attempt to keep pace with something much wilder, something that can't quite be tamed. And when you think about the speed of light, that ultimate cosmic speed limit, know that it isn't just a number, it's a boundary for time itself. Because as you approach it, time doesn't just slow from the outside, it begins to flatten from within. At light speed, time doesn't flow at all. For a beam of light, there is no before or after. It is born, and it arrives at the same moment. It doesn't wait, it doesn't age, it just is. That's why time slows as you approach the speed of light, because you're brushing against the very edges of temporal experience. The closer you get to light speed, the thinner your slice of now becomes. And for light, there is no slice, just instant connection between 2 points. But you're not light, you're here, warm, breathing, wondering. And that means you get to feel time, not just pass through it. You get to wake up and feel a little older. You get to watch sunsets and say things like, "It feels like just yesterday." You get to share a moment like this one across the air, across the stars, across a little stream of audio or screen light, with someone you've never met, but who's here with you, just the same. We may not be able to ride a beam of light, or touch the event horizon of a black hole, or glide through billions of years in the span of a single breath, but we can understand it, we can imagine it. We can gently wander through the ideas together, and that's almost better, because imagination, that's our own version of bending time, of folding distance, of reaching past the limits of what we are, to feel just a little more infinite. So as we drift quietly back toward the present, toward wherever you are, in your room, on your walk, curled up in bed, or staring out a window somewhere with a cup of something warm in your hands, just carry this with you. Time is not your enemy, it's your companion. It changes shape, it gives you depth. And even when it stretches, when it slows, when it doesn't quite behave, it's still with you, like a river, like a breath, like a heartbeat. You've just wandered through the edge of time with me. Thank you for that. I really do mean it. It's not every day we get to take a journey like this together, and you stayed with it. Through red giants and black holes and light-speed drift and the hush at the end of everything. If you're still feeling cozy, if your mind's still drifting gently, feel free to close your eyes now and let your imagination carry you further, or rewind. Or just sit in the quiet and listen to your own thoughts for a while. You're still moving through time, even now, just a little differently than you were before. And remember, there's always more to explore. Always more quiet mysteries waiting in the dark between the stars. I'll be here whenever you want to come back. Good night, or good morning, or whatever now looks like for you. And thanks again for drifting with me.